Hi, my name is Matiasz. I'm a PhD candidate in bioengineering. My home base is in the medical imaging informatics lab, but I also collaborate with Alcino Silva, who's a neuroscientist who invented research maps and now which has grown into a web app I'm going to tell you about. So a major task in science is to ask which experiment do we perform next, right? And when biologists ask this question, they need to tackle a different kind of big data than the one we're usually used to thinking about. And so what I'm referring to is, one, the enormous space of causal interpretations of a set of evidence, and also the enormous space of potential experimental designs we could pursue. And so I want to emphasize this, that the space can be very large, even if what we're dealing with is not traditionally big data, right? So even for a sort of personally curated knowledge base, the kind of set of papers that a scientist might base his next experiment on, it can be a very large space. And so one way to illustrate this is with the idea of causal graphs. And so even if you're not familiar with causal graphs, this picture will probably make some sense to you. We have radiation causing a genetic mutation, and the genetic mutation causes cancer, right? So this is very straightforward, but what's more humbling is the case where, let's say we have 3 variables and we don't know the causal structure between them. In theory, there are 64 possible causal graphs over 3 variables, right? So a very large space. And by the time this number actually grows super exponentially in the number of variables. And so by the time we get to something like 20 or 30 variables, there are more causal graphs to choose from than there are atoms in the universe. That's in theory. In practice, it's not quite so bleak, right? Because biologists employ a lot of domain knowledge and to constrain this model space. But there's still a lot of interpretations to consider. And so the question is, can we operationalize this? And so with research maps, we ask the question, what would it mean to navigate a space like this? Not necessarily causal graphs, but just the space of possible experiments we could do, the space of possible interpretations we could take. What would it mean to navigate this space systematically or intelligently or automatically even? And we ask this question in response to what we see to be a very glaring asymmetry in science, which is that we have very rigorous statistical methods for showing that our findings are significant, but we don't have any analogous procedure for showing that our planned experiments are optimal, right? So what would a mathematics of experiment planning look like? And so it seems that a solution to this problem would incorporate at least 2 features. And one is giving the biologists an intuitive visualization of the evidence that they could really navigate and explore. And the second is providing a very clear demarcation between what we believe based on empirical evidence and what we believe just based on a synthesis of the findings or sheer conjecture or background assumptions and so forth. And so with research maps, we try to provide both features. So this is an example, right? A research map is a graphical representation of empirical evidence and hypothetical assertions. And so the nodes represent phenomena that we're studying. The edges represent purported relations between those phenomena. And our research map's concision derives mostly from the simple taxonomy we use to categorize scientific evidence. So again, this is at a very high level of abstraction, but it captures much of biology. So we have 4 kinds of experiments. There are interventions and observations or non-interventions. In an intervention, right, we manipulate some agent and then look at its purported effect on a target. In a non-intervention, we simply passively observe the system and then see how a target responds or doesn't. And then within each of those classes, we have positive and negative. Positive simply means that the quantity or the probability of the agent increased, either through intervention or we just observed it to be so. And then the non-intervention case, the negative case is the quantity or probability of the agent decreased. So from these 4 kinds of experiments, we derive 3 kinds of qualitative relations. So between an agent and a target, there can be an excitatory relation, meaning more of the agent, more of the target, or less of the agent, less of the target. An inhibitory relation is just the opposite of that. So if you increase the agent, the target will decrease, and vice versa. And then we explicitly represent what we call a no connection edge, so an explicit independence between the phenomena, just to indicate that it's not, we have done an experiment, we found no connection between the entities. And so in this example at the bottom, we can see, based on the experiment symbols that we use, between this agent and target, we've done a negative intervention experiment and a second experiment, which was a positive non-intervention, and we've derived an excitatory finding. So these are all the components in the research map. We identify nodes with 3 properties, very generally: what, where, and when. The what just gives a taxonomic identity to the node, so it might be like the name of a protein, like Krebs, or the name of a behavior, spatial learning. The where locates the phenomenon in space, so maybe it's the CA1 region of the hippocampus, for example. And then the when locates the phenomenon in time, so maybe the experiment happened in adult mice. And of course, this is very general, and that's because we're trying as a first pass to accommodate lots of different kinds of scientific evidence, but in principle, you could link this up with any ontology. So our web app, for example, is linked to the NIF Neurolex lexicon of neuroscience terms, but you could plug anything into the nodes you want. Really, the emphasis is on the epistemological knowledge encoded by the edges. So again, between any 2 nodes, we have 3 kinds of connection: excitatory, which we show with a sharp arrowhead; inhibitory, which we show with a flat arrowhead; and no connection, which we show with a dotted line, circular arrowhead. The experiment symbols, as before, show the kinds of experiments that were done. So you could see between Krebs and memory at the top, we've done all 4 kinds of experiments. Between Krebs and LTD, we've only done a negative intervention. Finally, we have scores, and the scores are not probabilities, but they are our attempt to quantify the amount of evidence that we have from the literature for a given pair of phenomena. And I don't have time to go into a full derivation, but I can tell you that we use a Bayesian method to calculate the scores, and the scores were designed to capture 2 epistemological principles in biology, which are used very commonly, but often they're used implicitly. And so we're trying to operationalize them and express them mathematically. And those principles are consistency and convergence. So very simply, consistency says that it's good to do the same kind of experiment multiple times, right? To replicate your findings and to get the same results. So if that happens, your confidence grows, and the confidence grows like that, as you see on the screen. But there's a decay, right? Because the 50th iteration of an experiment is not necessarily as informative as the 2nd iteration. So there's some sort of decay. Convergence says that in addition to replicating your findings, it's good to do different kinds of experiments, for the simple fact that one of your experimental methods or more might be biased, and so the effect you're seeing might be an artifact of the experimental design, and so we try to mitigate that risk by doing different kinds of experiments. And if we see convergent results, we become more confident. And so with convergence, our score grows faster than with one kind of experiment alone, but again, there's a decay. So it's linear for the first 4 experiments, but for each round of 4 types of experiments, we'll see a lowering slope. So a key point is that with conflicting evidence, whether it's inconsistent or divergent, we'll have a lower score. And so consistent and convergent evidence will increase our score, conflicting evidence will lower it, and the edge that we visualize, whether it's excitatory, inhibitory, or no connection, is simply the edge relation for which there's the most evidence. So I said earlier that it's important to distinguish between the relations that we've shown empirically and the relations that we simply hypothesize. And so in research maps, we do that explicitly with hypothetical edges. And so these are edges that are shown in a lighter color, and we don't assign a score to them because they don't have any empirical evidence behind them. But they simply help to structure the empirical evidence or to contextualize the empirical evidence in the framework of some overarching hypothesis. So let's say, for example, we've done a few studies and we find excitatory effects between A and C, A and D, and B and D, right? But the background hypothesis is that the pathway actually runs A, B, C, D. But maybe we don't have the tools necessary to do experiments to demonstrate those direct edges. So we would enter those hypothetical edges into the research map, and now we can view the empirical evidence in the pathway, the 3rd diagram. We can view the empirical evidence alongside the hypothesis. And if you disagree with the hypothesis, you can change it and see how that would change the network structure. So everything I've shown you up to this point can be done very simply with pen and paper. But of course, as your knowledge base grows, it becomes increasingly impractical. So we've developed a web app, Research Maps, which you can access at researchmaps.org. It's free. We have currently around 600 users across 4 continents. And it's just simply a web application for making research maps and querying the research maps that you create and the public research maps of other collaborators or other users. And so there's really 2 main pages in the system. One is what we call the article page. And so for each article that you map, each article for which you create a research map, you can have a dedicated page. And so this is one example of an article from Nature. On the left, we have a simple form for inputting all of the fields that I just enumerated for you. It doesn't take that much more time. I mean, it is currently manual, but people actually find it quite instructive to go through the exercise, even with papers that you think you know quite well, to just actually go through this taxonomy and enter the evidence that it actually encodes. And then a research map will be drawn for you, which can encode one or more experiments on each edge. Having entered a bunch of papers, now you might want to query the entire map that you've entered, and so we can concatenate all the maps you've entered and the maps of other users, and you can query those maps in a global map. So you can search for a specific phenomenon, you can search for a specific relation between two phenomena, or you can search for ranges of evidence. So maybe you're only interested in edges for which there's very little evidence or a significant amount of evidence. And so Alcino Silva, who invented research maps, has been using this system for a number of years, and it's amazing how large this knowledge base can grow. So most of the time now when he reads a paper, he'll enter in the research map, which takes only a little extra time. And just in the field of memory allocation and some related literature, here we have 125 articles, over 2,000 experiments, over 1,000 nodes, over 1,600 edges. And so now this is a very rich global map that he can query for specific features. And again, it's not just the ontological information about what these things are and what they're doing, but the epistemological information. So how did we come to know these findings? And we can now quantify what percentage of the experiments are interventions versus observations. Where have we not done a negative intervention where we might want to do one? Here's all of his evidence only involving CREB, just one specific node, so you can see plenty to think about. So if you're planning an experiment, holding this in your head is quite a task. But if you can visualize it in a way that you can navigate it, it becomes much more easy. So in current work, we're trying to sort of extend this workflow in both directions. By that I mean, right now entering the maps is manual, but we'd love to automate it so that we could just map all of PubMed, for example. And so my colleague Justin Wood in computer science is looking in ways to automatically extract research maps from PDFs. So you would just feed the system a bunch of PDFs. It would generate a map for you. Likely the map would be noisy, but then you could then just simply edit the map in a supervised sense rather than having to create one from scratch. On the other end, I'm working on automated experiment ranking. So asking the question, just as we have a statistics for quantifying the significance of a finding, can we quantify the potential information gain of a new experiment? So given the current knowledge base that we have, what would it mean to rank experiments by how much information they could provide? So these are our collaborators, and I'm happy to take any questions. Thank you.